Today we're going to be talking about changing representations of vectors. This is something that we've talked about before, so in theory you already know how to do all of this stuff, but we're going to be talking about it in a different context today. Before we talked about how to represent a linear map with respect to two bases of your domain and codomain. So I'm going to recall some stuff about representations of vectors, and I'm also going to use some notation that the book uses a lot, but I haven't used a lot in class, but it's going to be useful for us today in this section. So recall the representation of a vector v with respect to a basis whose basis vectors are b1 through bn. The representation basically tells us how can we write v in terms of the vectors b1 through bn, in other words, like a linear combination of b1 through bn. And so how we do that, so if v is equal to c1b1 plus up through cnbn, then the representation of v with respect to b1 through bn is just the coefficients c1 through cn just thrown into a vector, an n entry vector. So c1 through cn is the representation of v with respect to b. Let's do some examples. It is important to recall that, or to know that representations depend on the basis. So if I want to use b is equal to the standard basis, so 1, 0, and 0, 1, and d is going to be the basis whose vectors are 1, 1 and 2, 3. These are both bases for R2, and I'm going to represent the vector 7, 9, which I'll call v, with respect to both b and d. So to do this, I have to write 7, 9 as a linear combination of these two basis vectors, which of course is equal to 7 times the first basis vector plus 9 times the second basis vector. And so the representation would be 7, 9. So I have that down here. The representation of v with respect to the standard basis is 7, 9. Which is interesting because actually what we're saying here is that the vector is represented by itself with respect to the standard basis. So that's an important general statement. So any vector with respect to the standard basis is represented by itself. But of course, if I look at a different non-standard basis, that won't be true. So 7, 9 with respect to the basis 1, 1, 2, 3 will be, my representation will be different. And you could go solve this out on your own to figure out what your C1 and C2 would be, but I just have it here for you. So 7, 9 is equal to 3 times the first basis vector plus 2 times the second basis vector. So its representation with respect to d is going to be the vector 3, 2, because those are the coefficients in that linear combination. All right, so let's talk about representing maps. So for the linear map, which we'll call f from R2 to R2, we can represent f with respect to bases b for R2 and d for R2. And of course, you could replace R2 with we could replace our domain and codomain by just arbitrary vector spaces v and w. So anyway, we can represent this map as follows. So if f of b1 is equal to c1 d1 plus c2 d2, and f of b2 is c1 prime d1 plus c2 prime d2. In other words, what I'm saying here is I am looking for the representations of f of the basis vectors with respect to the basis d for R2 for my codomain. So using our notation that we just talked about, what I'm really saying is that f of b1 is represented with respect to d by c1, c2, and the representation with respect to d of f of b2 is equal to c1 prime, c2 prime. Then f is represented by the matrix A equals c1, c2, c1 prime, c2 prime. So what we're really doing here is we're just taking our representation of the first basis vector, throwing it into the first column, and our representation for the second basis vector, throwing it into the second column. And of course, this generalizes if I had n basis vectors for B, then there would be n columns here, all given by the representation of the basis vectors. All right, so now looking forward to today, we're going to do all of the same stuff that we did up here, but we're just going to do it using the identity map, which I will denote by I from R2 to R2. The identity map just sends every vector to itself. So identity of V is equal to V for all V in R2. So now I'm really just rewriting everything except everything that is in black is just in the context that I want to look at for today. So for the identity map, I from R2 to R2, we can represent the identity map with respect to B and D bases for R2 by saying if B1 is represented with respect to D by C1, C2, so the representation of B1 is C1, C2, and same for B2. B2 is equal to C1 prime D1 plus C2 prime D2. In other words, B2, the representation with respect to D of B2 is equal to C1 prime C2 prime. Then the identity is represented by, sorry, this should just be I. Sometimes people use the notation ID to represent the identity map, but I should just have an I because that's what I've been calling it here. So I is represented by A equals C1, C2, C1 prime, C2 prime. In other words, the representation of the identity can be put into a matrix where the columns are just given by the basis vectors being represented with respect to our other basis D. Again, this should just be an I. So anyway, you might notice that in the above, we were using f of B1 and f of B2, but since I'm using the identity map where, so I could have written I of B1 here in order to be more consistent with what I was writing up here. But of course, the identity map says that identity of anything is itself. And so I was just dropping that because the identity of B1 is equal to B1. So really what we're doing here is we're just rewriting B1 and B2 in terms of the basis vectors from D. Okay, this is kind of abstract. So we're going to do an example soon. But just to give you the definition of what this actually is, well, so this representation matrix that we came up with right here, what we call this matrix is the change of basis matrix with respect to the bases B and D. So for vector space V and bases B and D for V. We can always look at the identity map So the identity is just the obvious map from V to itself, sending each element to itself. Could just do I here, but it doesn't matter. So anyway, this is just called the change of basis matrix. The book makes a point that I agree with, that a better name for this would be change of representation matrix, but I understand why it was called change of basis matrix in the first place. But really I think it's a little bit more helpful to think of this as a change of representation matrix because that's really what the matrix does. Let me show you what I mean with an example. All right, let's do R2 like we were talking about before. So for R2, we'll have B is equal to 2, 1, and 1, 0. That's our first basis. And D is the basis with negative 1, 1, and 1, 1. So the first thing we have to do is write, so we're trying to represent the identity map from R2 to itself. And so the identity of 2, 1 is equal to 2, 1. So we want to write 2, 1 as a linear combination of the basis vectors from D. And I went ahead and did this for you. 2, 1 is represented by the vector negative a half, 3 halves with respect to D. Similarly, the second basis vector, we can write that as a linear combination of the basis vectors of D. And that linear combination's coefficients will be negative a half, positive a half. Okay, so given this, the change of basis matrix, so in general, it's always going to be given by, the columns are going to be given by the representations of the basis vectors 2, 1, and 1, 0 with respect to D. And so here, what we would get would be the first column would be negative a half, 3 halves. And then the second one would be negative a half, positive a half. And so this is our change of basis matrix for R2 with respect to the bases B and D. Okay, so let's consider V is equal to 7, 2. If I wanted to write V with respect to B, so I write it as a linear combination of 2, 1, and 1, 0. I can write it as 2 times 2, 1 plus 3 times 1, 0. Okay, so the representation of V, of course, would be equal to 2, 3. Now, if I want to write V in terms of D, I can use the change of basis matrix. This is actually what the change of basis matrix is for. So really what I am saying here is that I can figure out what my representation of V is equal to with respect to D. So what I'm going to find here is the representation with respect to D of V. And what that's going to be equal to is our change of basis matrix, which was negative a half, 3 halves, negative 1 half, 1 half, times our representation of V with respect to B, and this is equal to, let's see if we do this. So I would have 2 times negative a half plus 3 times negative a half, which is negative 1.5. And then for my second entry, I would get 3 halves times 2, that's 3, plus 3 times 1 half. I'm just going to write 1.5. So that is equal to negative 2.5, 4.5. So anyway, this is our representation of v with respect to d. So that tells me that v is equal to negative 2.5 times d1 plus 4.5 d2 d1 of course is equal to the vector negative 1, 1, and d2 is equal to the vector positive 1, 1. So just to sort of check our work here, I would want to check that this linear combination is actually equal to v, which we already know that v is the vector 7, 2. That's what we started off with. And if I were to do this out, I would have, so first entry would be positive 2.5 plus 4.5. That's equal to 7, so that's good. And then negative 2.5 plus 4.5. 4.5 minus 2.5 is equal to 2. So of course, these two things are actually equal like we want, but we now know how to write v in terms of the basis vectors for d. And of course, we could do this for any vector v that we can first represent with respect to b. Okay, so this next lemma just summarizes what we just talked about at the end of that example. Left multiplication by a change of basis matrix. So representation of the identity with respect to b and d. This is our change of basis matrix. And left multiplication, like right here, converts a representation with respect to b. That was this right here. Changes that, converts that to a representation with respect to d. And so that's what we found right here. So we found that representation of v with respect to d is equal to negative 2.5, positive 4.5. And we just get that by taking our representation with respect to b and doing left multiplication by our change of basis matrix. So shorthand for this is that representation with respect to d of v is equal to our change of basis matrix times our representation with respect to b. Conversely, this is not something we talked about in the previous example. If we have the representation of a vector with respect to d is equal to some random matrix M times representation of v with respect to b, so M is just some other matrix that satisfies this, then M has to be a change of basis matrix. This should be for all v, by the way. Okay. So here's another lemma that is not obvious, but you can take as fact. So a matrix is a change of basis matrix if and only if it is a non-singular matrix. So change of basis matrices are non-singular or invertible matrices. So a corollary is that a matrix is non-singular if and only if it represents the identity with respect to some pair of bases. And that's sort of just rephrasing things. So it's really just rephrasing this lemma here because it says that a matrix is non-singular if and only if it represents the identity map, blah, blah, blah. But this all is just the definition of a matrix changing bases. So that's what I wrote right here. So M is a change of basis matrix means that M is equal to the representation of the identity map with respect to some pair of bases B and D. So here are some practice problems. Find the change of basis matrix for this matrix, for this basis B and this basis D. Note that D is the standard basis for R2. Use it to write this vector right here. So this is already a linear combination of the basis vectors from B. So use the change of basis matrix to write this vector in terms of the basis vectors from D. I should mention that it is pretty easy to actually find a representation of this matrix with respect to D without using change of basis matrices. And that's because, so if you just actually combine terms here, so this is equal to 414 plus 412. This is equal to 826. If I want to represent this with respect to the standard basis, something we talked about at the beginning of this section was that any vector is represented by itself with respect to the standard basis. So the representation of 826 with respect to the standard basis is 826 itself. In other words, it's equal to 8 times D1 plus 26 times D2. Anyway, I use the standard basis because I want to make this process a little bit easier. So try working this example out on your own right now. And then, so pause the video, try to work it out. And then when you're done, then we'll go over it. And then once you're, after we go over that, then we'll go over the second one. Okay. Right, so before I talk about the second problem, let's just do the first problem. All right. So the first thing I need to do is write the vectors from B as linear combinations of the vectors from D. And this is equal to 2 times the first basis vector plus 7 times the second basis vector. And same thing for 1, 3. That's equal to 1 times the first basis vector plus 3 times the second basis vector. So our change of basis matrix is going to be, I'll just call it M, equal to 2, 7, 1, 3. And now I can use this to write this linear combination in terms of, I want to now represent it with respect to D. So, right, so what do I do? What I do is I take my change of basis matrix and I'm multiplying on the left by my representation of V with respect to B, which is 2, 4. And so this is equal to, so I get 2 times 2 plus 1 times 4 for my first entry, and 2 times 7 plus 3 times 4 for my second entry. This is 826. So V is equal to 8 times the first basis vector plus 26 times the second basis vector. And that is what we expected to happen from our previous conversation. So that's how you do that one. All right. Now, for the second problem, to decide whether or not this matrix is a change of basis matrix. So I'll let you think about that one. That one should not take as long, but give it a shot. And when you're done, unpause the video. Okay, so let's go over. All right, to decide whether or not something is a change of basis matrix with respect to some pair of bases, what we can do is use the lemma up here. So a matrix is a change of basis matrix if and only if it is non-singular. So I need to decide if this matrix is non-singular or not. So I'm just going to copy and paste it. And this, I can do a row reduction here. I could take -2 times row 1 plus row 2. So I get 1, 2, 3. Sorry, that should have been a -4 so that I can make this a 0. That'll stay 9. I really just want to put this in echelon form. Okay, so if I do -4, then this entry will be a 0. -4 times 2 is -8, plus 5 is -3, and -4 times 3 is -12. This would be -6. So anyway, this is in echelon form, and it has 3 non-zero pivots here. And so this is a non-singular matrix. It's row equivalent to the identity matrix. You could do more row operations to show that it's row equivalent to the 3 by 3 identity matrix. I'm just going to stop here because it's already in echelon form. Therefore, our original matrix is a change of basis matrix. And that's it. So in the next section, we will continue using this and just furthering this a little bit more. Let me know how the sound quality of this one was. I'm using a slightly different approach to recording, and hopefully it goes well. Anyway, thanks.